So what else can we do with sets other than talking about an element being in a set or being not in a set? Well, we could talk about relationship between two sets. And relationship between two sets is determined by the behavior of their elements. So, for example, one useful notion is of one set being a subset of another, which just means that all the elements of the first set are in the second. For example, all dogs are mammals. So the set of all dogs is a subset of the set of all mammals. And moreover, since there are mammals other than dogs, like humans, in this case, there are elements of the set mammals that are not elements of the set dogs. So dogs is a proper subset of mammals. So we say that S1 is a subset of S2 for any two sets if all elements of S1 are also elements of S2. And we say that S1 is a proper subset of S2 if there is also some element of S2 which is not in S1, like with dogs and mammals. On the other hand, it could very well be that S1 is a subset of S2, but all elements of S2 are also in S1, so they're both subsets of each other. In this case, we say that those two sets are equal. So if S1 is a subset of S2, there are two cases. Either they're equal or S1 is a proper subset. So one useful visualization when we're talking about sets is to draw pictures, circles, and so on, to indicate what sets we have, where elements are, and most importantly, how the sets overlap or don't overlap. So when we draw them, this is called Venn diagram. We usually start by drawing a square, which is our universe. For example, it can be all people, all numbers, all animals. Then, inside of that universe, we represent every set as a circle. For example, a circle for dog, a circle for mammal, circle for birds. Well, okay. They don't have to be circles. You could draw them as some kind of squish circle, oval shapes too, if you need to. But generally, they're like circle-like shapes. And then we put dots to represent elements. For example, if you are talking about bank tellers and feminists and Susan, we could put a dot in the feminist but not in bank tellers representing Susan, who is feminist, well, when she is a feminist but not a bank teller. We draw one circle or whatever, an oval, inside another to represent a subset, because that means that everything in, say, dogs is inside of the set of mammals. On the other hand, sometimes there are no common elements between two sets, in which case we say that the sets are disjoint, and then we will draw them as non-overlapping circles. So here you see on those two Venn diagrams three possible scenarios. Bank tellers and feminists overlap, but there are bank tellers who are not feminists, and there are feminists who are not bank tellers. Dogs is a subset of mammals, and the set of all birds is disjoint from the set of all dogs and actually from all mammals. In two sets, we can actually construct new sets out of the set that we are given. So let's start by doing an example. Suppose you have a set A containing 1, 2, and 3, and a set B containing 2, 3, and 4. So first of all, those two sets overlap, but neither of them is a subset of the other. So what can we do with them? Well, we could think back to our logic operators and define a set containing everything that's in either A or B with the or in both A and B with the AND operation. So the AND operation in a set theoretic notation is called the intersection. The intersection of two sets is all elements that are common to both sets. So for example, 2 and 3 are in A, and also 2 and 3 are in B, so intersection of A and B would be 2 and 3. If you take an OR instead of an AND, we end up with a union of two sets. So this is all numbers that are in A or in B. For example, 1 is in A, 2 and 3 are in both, and 4 is in B, so all of them are in the union. We could also look at the numbers that are in one set but not in the other, and this is called the difference. And there would be two differences, elements of A that are not in B and elements in B that are not in A. In particular, elements of A that are not in B is just number 1. If you want to talk about the difference without thinking, is it elements of A not in B, elements of B not A, just everything that's not in the intersection, it's called the symmetric difference. So the easy way to think about is if you take an intersection and if you take a union, and then everything that's in the union but not in the intersection of two sets is in their symmetric difference. And finally, given a set, we could take a complement of that set, which is all elements that are not in the set. And here it's crucial to have a notion of what your universe is, because if my universe is all natural numbers, then the complement of the set 1 to 3 is, well, all natural numbers except for 1 to 3. But if my universe is all digits from 0 to 9, then the complement of 1 to 3 would be 0, 4, 5, 6, 7, 8, 9, different set. So let's play a little bit with those notions, and both with notions of the set operations and the subset. So suppose we have A, which is a subset of B. How do you think the intersections in union are going to behave? Well, first of all, if A is a subset of B, then everything that's in A is already in B. Then all elements that are in both A and B are just all elements of A. So intersection of A and B is just A. Similarly, union of A and B is just B because, again, there is nothing in A which is not already in B. Difference A minus B is empty because there is nothing in A that's not in B. But then there is a difference B minus A, which is all elements of B that are not elements of A. So here's the puzzle for you to think about for next time. And next time we'll say why we are talking about a puzzle like that when we are doing sets. So suppose that this semester 160 students are taking COMP1000 and 105 students are taking COMP1002. As you know, a lot of you might be taking both of those courses in the same semester. So suppose that the total number of students in those two courses, the total enrollment between those two courses is 200 students. From here, how would you derive how many students are taking both COMP1000 and COMP1002?